Hey guys, this is Vaishak Pillai and welcome to Embedded In. So today's topic is secure connectivity. Let's start by creating a simple HTTP page that we can serve through a local server. So we do vi index.html, and on that we are going to have a simple HTML page. We put the start and stop tags for HTML, and we're just going to have a simple body with the close tag here, and we're going to say that we just have a h1, a heading which says hello embedded in. Alright, we save this and we're going to bring up a dummy server using a Python module. So we say Python 3 -m for module http dot server, and we want this to come up in port 80. I need to give sudo permissions. Sudo, that is because I'm using port 80. If I was using a different port, that shouldn't have been a problem. So the server is up. Now let's go to a browser and see whether the page is getting served. So I open the browser. I'm going to type in localhost. So we can see that the page that we created has been served. And if we go back to the server, we can see that there has been a request which has been served. Now what does the server request actually look like? You press F12, which opens up the debugger, and I'll reload the page. So it's a very simple HTTP request. The request has been for /. The default is index.html when the path is not specified. And the response is here. It's the same HTML page that we created. Now the question is, how did the browser know which server to reach when I gave localhost? So in the case of localhost, it's a standard name which the operating system knows. So localhost will map to 127.0.0.1, which is the local interface. Now, had I given google.com instead of the localhost, say I give google.com, how will the browser know which server to connect to? We know that an IP address is required to connect to a server. So to translate this name, this domain name into an IP address, there is a process called DNS resolution. You can visualize DNS resolution as a simple process wherein there is a DNS server which has a huge table of all the domain names and the corresponding IP addresses. And when the browser asks the DNS server for a particular domain name's IP address, he'll fetch this IP address and provide it back. We can see this in action. Let's close the server and clear the screen. Let's do dig of google.com. The name got resolved, and this is the IP address that the DNS server returned. Let me copy this in the browser. Let me close the network analyzer. I'll just directly give the IP address and we go directly to google.com. Now the next question is, DNS is also a server which has an IP address. How did the browser know which DNS server is to be contacted to get the IP address of the domain name that you are requesting? So back in the console, we can see that in this case, the server, which is a DNS server here, is 192.168.0.1, which is nothing but the router to which my PC is connected. When a device connects to the access point, or the router as we generally call it, a DHCP request is placed, and as a response to this DHCP request, the device is issued an IP address and a bunch of info is passed back to the device. This includes the DNS server to use. In this case, because I'm connected to my home AP, I know that I have configured the right DNS server here. Say you walk into a coffee shop and connect your phone to the coffee shop access point because you saw that they have free Wi-Fi, and you try to connect to a banking website to transfer some money from your phone. So in the browser, you give bank.com. This request goes to the coffee shop access point, and the access point will say bank.com is at say 200.16.30.12. All this is happening between the phone and the browser. So the browser will place a request to this server, You get a beautiful website which looks just like your bank.com, which asks for your username and password. You enter the data here and you get a message that because of a temporary issue, bank.com is not reachable at this point. You have already entered your username and password and you feel that this is a temporary network issue because of which you are not able to connect to the bank site. But what actually happened in this case is that a rogue DNS server was configured in the coffee shop access point, and the address that you got is not actually bank.com. It is in fact something which looks like a bank.com. It's a phishing site which is hosted by an attacker. Now you just entered your banking username and password into a rogue site which has logged it, and they'll be able to use this to access your actual banking account. The same can happen when your device wants to connect to the cloud. Say the device wants to download an OTA image, connects to the cloud, fetches an image and flashes it. But just that instead of the actual cloud instance that you have configured, it might have connected to a rogue instance because there is no means to verify whether this is the actual cloud server. It downloaded a rogue image, which can potentially make this part of a botnet. So to avoid all this, we need a cryptographically safe way of verifying the identity of the server that you're going to connect to. Let's build a protocol for this. Assume that as part of the connection to the server, let us consider that this is the server, and let's have a client here. First, when the client connects to the client will ask the server to present a calling card or a visiting card of sorts from the server. So the server will present its calling card, which has two main pieces of information. Say, like in the previous case, let's assume that the server is bank.com. The calling card will have this info that it is for bank.com and that there is a public key for which the corresponding private key is kept safely inside the bank.com server. So the private key is inside the server. Nobody has access to that private key. When the client receives this calling card, he sees a public key here. Now, we don't want some other guy to download the certificate and tell that, okay, this is my calling card. You can trust that it is bank.com itself and send me your username and password. To avoid that, the client will generate a challenge. The challenge is nothing but a random number which has been encrypted using the public key that was there inside the certificate. This will be sent to the server. The server will use its private key and decrypt the challenge and send back the random number it gets as part of the decryption. Now, only if the server has access to the private key, which is paired with the public key that was there inside the calling card, will it be able to successfully decrypt the challenge and generate the same random number that was originally encrypted in the challenge by the client using the calling card public key. This way, the client can be sure that whoever sent this calling card has access to the private key corresponding to the public key that was there in the calling card. An attacker will not be able to do this whole operation by just having the same calling card, say, sniffed out of a network, and in the phishing server, they cannot keep the same calling card and assume the identity of bank.com because they do not have access to the private key corresponding to this public key. But then the question is, why can't they just create a new calling card which says he is bank.com and put in a public key for which they have access to the private key? So for this to be effective, we need one more step in this whole process. We can have the client store a copy of the expected certificate that is supposed to come from bank.com, which also has the public key. When you connect to bank.com, he'll provide you the certificate that he has or the calling card that he has. The client can compare the certificate that he has with the calling card that is coming in from the server, and if the public key and all the other info matches, then he can proceed with the connection to the server. Now, even though this can work theoretically, there are two practical difficulties. One is, how do we get the certificate that they can trust and store in the first place? And second is, it's highly impractical to have the certificates of all the servers that you might potentially connect to. So to address this, we introduce a third party called a certificate authority. So unlike in the previous case where the bank.com server created a certificate or a calling card on its own, because we have introduced this third party, when bank.com wants a certificate, he'll put in a bunch of information into a document. He'll say that my name is bank.com, this is my public key, etc. etc. This whole document, which is called a CSR or a certificate signing request, will be sent to the CA along with a bunch of physical documents. The CA will first verify the physical documents and ensure that this CSR is in fact coming from the legal bank.com organization, and then start attaching a bunch of information to the CSR. The first thing is some sort of an identity. Let's call this as the CA ID. This is the identifying information with which somebody who gets the bank.com certificate once the CSR is signed can track back and figure out who issued this certificate. Once this is added, a hash of the CSR will be computed, and this hash will be encrypted using the CA private key. Once it is encrypted, this is called a thumbprint, and this thumbprint is attached to the CSR. Once this whole process is completed, the CSR has now been converted into a digital certificate. Now, CAs are typically large organizations whose business is to ensure that this whole process is secure, that they do all the due diligence in verifying the physical documents and make sure that they don't issue a certificate to the wrong person. They also have to follow world-class practices to make sure that the private key that is used to encrypt the hash and issue a certificate from a CSR is kept extremely safe. And it is not just bank.com. Any organization who wants a digital certificate can approach the CA and get a certificate issued by proving their identity and paying the required fees. Now, the advantage is that the CA would have issued, say, hundreds of certificates, if not thousands. And to trust all these individual certificates, we just need to trust this one CA. And the fact that the certificates C1, C2, etc., which are issued to different organizations, can be mathematically verified if we have access to the CA's certificate. Let's see how that happens. So now, unlike before, where we had to have access to the bank.com certificate to validate what is coming in from the bank.com server, we just have the CA certificate. So the client or our browser has the CA certificate inside. You connect to bank.com. Bank.com will present the calling card, and in this calling card we'll have the information about bank.com, the identifying information, the public key of bank.com, and also the CA ID, telling that this calling card, or the digital certificate in this case now, that I'm presenting has been issued by this particular CA. The browser will have multiple CAs in there. So it is not just one CA that is there out in the world. There are multiple CAs. So when the browser receives this calling card or the digital certificate, he will look at the CA ID, find the corresponding CA. When we say we have a CA, it is the CA cert that is stored inside the browser. Now the browser will compute the hash of all the data inside the calling card except for the thumbprint. Keep that safely. And use the CA's public key, which is there inside the CA certificate, to decrypt the thumbprint. Once it is decrypted, the output will be a hash, and if these two matches, then the info that has been put into the CSR by bank.com has not been compromised. Here the information says that this is in fact bank.com and that you can trust it. And now we know that the certificate that is presented by the server was in fact issued to bank.com by a CA that we trust. Now we can go with the challenge response mechanism and all that, which involves the public key that is coming from this certificate. But at this stage, we are sure that the private key corresponding to this public key is in fact in a server, which is the authenticbank.com server. So you would have noticed that this is not absolute trust. It is just that we are offloading the trust to a CA. Now in a practical case, where are these CA certificates sitting? Let's take a look. So in the browser, I can go to options and search for certificates. You can click on this view certificates and you'll see that there are a bunch of inbuilt tokens that are present inside the browser. Let's take this Baltimore certificate for example. It says that this is the certificate from Baltimore and it has been issued by the same person because it's a self-signed root CA certificate. We can also see that there is this public key info which we can use to verify other certificates that are coming in, which says it has been issued by this Baltimore Cyber Trust root. Now let's see how this works. Let's go to google.com. The browser says that he is able to verify the authenticity of this site, that in fact this page that we are seeing is coming from a server that the browser trusts to be from google.com. So it says the connection is secure. We click here. We say that it has been verified by Google Trust Services. Let's go to more information. In the security tab, you can see view certificate. It says that this google.com site has a certificate which is issued by, let's see who is the issuer. Issuer name is Google Trust Services using the GTS CAS 101 certificate, which is here. Now this is an intermediate CA. So the root CA in this case is GlobalSign. GlobalSign issued a certificate to Google Trust Services and said that I trust you enough to start issuing certificates on your own, and even if somebody doesn't have the intermediate certificate, they can come back and verify the intermediate certificate using the original root certificate, which is here, which is again self-signed. The GlobalSign certificate has been issued to GlobalSign by GlobalSign. So this is called a chain of trust. So when the browser first gets this certificate, he'll look at the authority key identifier, which is 98D1 here. He'll look at the set of inbuilt tokens and use that issuer key identifier to identify which certificate needs to be used to verify the trust. So in this case, he should be having the Google Trust Services here. Yeah, it's here. Had this not been here, he'll go one level up and see the certificate here. So we can see that the subject key identifier is 98D1 and this has been issued the certificate by this guy 9BE2. He'll go back, search for 9BE2, he'll come with GlobalSign, and this 9BE2 which has been issued by 9BE2 is the root level certificate. Now if at least this is not there in the set of trusted certificates, we'll get a red padlock telling that the connection is not secure and the browser will not let you go to that site for your own safety. So this whole process is just a small part of the entire TLS flow that happens when a device tries to connect securely to the cloud. We took the browser as an example to explain this flow just because it is easier to visualize the flow here and see the certificates in action. But even in an embedded system, these certificates or the root certificate that you trust need not be a global root certificate. It can be just something that can be used to verify the authenticity of the server that you're connecting to. That needs to be baked into the device so that when a TLS connection happens, that root of trust can be used to ensure that the connection that you're making with external servers are secure. Thank you for watching. Have a nice day.